This lesson is for FST, Lesson 6.3 on the Multiplication Counting Principle, or MCP, and Independent Events. We're going to start with the Multiplication Counting Principle, which states that the number of ways to choose one element from set A and one element from set B is to simply multiply the elements together. You could also multiply the probabilities together. Most of the questions you're going to see here today are going to be just multiplying the elements, not multiplying the probabilities, but know that the probabilities could be another option. Most of the time when I teach kids about how to choose or how to decide when to use the MCP, I tell them to think about whether or not it's a license plate question. In the state of Minnesota, when they generate a license plate for each individual or each individual vehicle, they use combinations of letters and numbers. We're going to focus on the current configuration that's shown here for the number, letter, letter. I realize that there are other possibilities for license plates, including vanity plates and military plates and all kinds of other options for how plates could be configured, but we're going to stick with the generic version here, which does 3 letters and three numbers and then 3 letters. And so when kids generate questions like this one, it's nice to have a visual reference here of a bunch of blanks, and the blanks represent what we're going to be multiplying together. So in the first spot on your license plate, if we're doing number, letter, letter, the first spot could be any of the digits from 0 through 9. That means there's 10 different numbers that I'm choosing from to go in that first position. Since repeats are allowed on license plates, I would have still 10 available for position number 2 and for number 3. So far, if I'm trying to do a number, and then another number for my license plate configuration, I would have 1,000 different ways of arranging 3 digits. For letters, there's 26 letters in our alphabet, and again, repeats are allowed. So if I did 26 times 26 times 26, that would give me all the different combinations of letter, letter. Again, because repeats for letters are allowed. And so to get all the combinations of letter, number, letter, I would just simply multiply all of those together. So I'd say 10 to the third times 26 to the third. Hopefully you know that 10 to the third is 1,000, so you could simply type in 26 to the 3 times 1,000. And when you do that, you get 17,576,000. Now that is not a probability, that is simply how many different license plate combinations there are for this particular configuration. So that doesn't necessarily tell us all the different outcomes for all license plate in the state, but it does tell us for this particular setup. If we were looking for the probability of this exact license plate, we know that there's only one of those that would be generated with the numbers 1, 2, 3, and then ABC. So we would simply do 1 divided by 17,576,000, and that would tell us the probability. Some other questions that students might encounter are more mathematical in nature, or more like what you would see in this class. How many different outcomes are possible for rolling a fair 6-sided die and spinning a spinner with 4 sections? So in this case, we only have 2 things we're worrying about instead of 6 on the previous. We've got a die and we've got a spinner. So on the die there are any numbers from 1 through 6 available, and on the spinner there's 4 sections. They have to tell us that or give us a picture of the spinner. So we know that there's 4 there. So when we multiply together for the multiplication counting principle, we get 24 different outcomes. It's nice to know that number because if I ever asked you to list the sample space for the die and the spinner, now you know how many items in your sample space there will be. Next question asks, how many different sets of answers are possible for a quiz with 10 multiple choice questions, each with 4 choices, and 2 true-false questions? And then make sure that you answer the additional question here of what is the probability that you'll be able to guess and get all the answers correct? So each question gets an answer blank. 1, 2, 3, 4, 6, 7, 8, 9, 10. So that's for the multiple choice, and then I've got 2 true false. So I'm going to label those just to help you visually see what we're doing here. So these are all multiple choice. And since there are 4 choices available, like A, B, C, D, I've got 4 choices on each of these. And so as you continue here, you'll see that we end up with a base of 4 multiplying by itself 10 times, so that would be the same as you raising it to the 10th. When you do when you do true false, those only have two options. So I'd multiply by 2 squared. Or you could say here that you're doing 4 to the 11th, because 2 squared is 4. 4 to the 10th times an additional 4 would be the same thing as doing 4 to the 11th. 4 to the 11th is 4,194,304. So that tells us how many different sets of answers are possible. Only one of those combinations is the correct answer or the answer key. So what's the probability that you'd be able to guess and get all the right answers? 1 over that. So that's where the probability comes into play here. You might use the total number of outcomes to help you figure out the probability. Usually that big number that you get will be the bottom of your fraction. The next question is simply a review for students on how to draw a tree diagram. Students should pause the video and draw the tree diagram, and then I'll ask them a follow-up question. So if this were the tree that you came up with, hopefully you would say that this tree would not be given full credit. Looks like this person ran out of room when they got to the far right here, and so they just tried to squeeze in their answers, and now all of a sudden their answers are not completely lined up. So even though this is a correct answer, it probably would not receive full credit. So let's fix it so that it does look the way that it should. You want to make sure that all your branches are nice and lined up. Everything on this bottom row is nice and lined up. Keep in mind that I used A for pasta. You should not use the letter P because you've already used it here. If we were using variables, anytime you use the same letter, it means the same thing. So please use different letters for each one of these. If you chose a different letter for pasta than what I did, as long as it's clear what you're using and why, it shouldn't make a difference. So this was not an MCP question. This is a review from 6-1 on how to do a tree. Let's turn this into an MCP question now by asking the question, how many different meal combinations are there? There are two ways to answer the question. The first way is by using the tree. If you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, you would be correct, and that would be a perfectly fine way to find your answer. However, if you were trying to utilize the MCP or the multiplication counting principle to answer the question, you'd still get 18 as your answer, but you'd find it in another way. Keep in mind that when you do the MCP, you're listing out blanks for what you have. And so let's label what we have. We have entree, beverage, and dessert. So there's 3 pieces to the meal. We would multiply the different outcomes together. For the entree, you have 3 different options. For the beverage, you have 2, and for the dessert, you have 3. When you multiply 3 times 2 times 3, you get 18. So while the number of outcomes is 18, the reason is because of the MCP or the multiplication counting principle. There's 3 times 2 times 3 options, so you know there's going to be 18 total outcomes. So the multiplication counting principle is helpful because it helps you determine how many total items you should be expecting when you draw the sample space. Our other topic for today is independent events. When events are independent of each other, their probabilities do not affect each other. It's a pretty easy definition. Keep in mind, however, that regardless of you remembering or knowing the definition of independent events, you always verify it mathematically. So it's important for students to memorize this formula. Take the probability of A times the probability of B. And in order for the events to be considered independent, it would have to be equal to the 2 events' overlap or intersection. So when I have kids memorize the formula for independent, we take away the parentheses and the P here, and we simply say the intersection is equal to the probability of A times the probability of B. When you're deciding if the events are indeed independent, you want to see if the one side is equal to the other side. If they are equal, then you're going to say that they are independent. If they are not equal, then you're either going to say not independent or you could say dependent. So some examples to help illustrate the definition of independent. If it snows today, does that affect at all whether or not your pencil will break? Absolutely not. We all know that those two things are completely independent of each other. That's a pretty straightforward, logical example. More mathematically related, if I roll a 1 on a single die on my first roll, that has no bearing and does not affect whether or not I'm going to get a 1 or a 2 or a 3 or any other number on my second roll. Getting a 1 the first time doesn't necessarily mean I'm more or less likely to get a 1 or not on the second roll. So rolling a die is a clear indicator of independent events. A deck of cards, however, can be either way depending upon how you handle the situation. In our example of independent events, we would say that the probability of drawing an ace and the probability of drawing a 2, those are independent events if you replace the card after your first draw. And we'll contrast that to what happens if you don't replace the card in just a moment. So some non-examples, things that are not independent because they do affect each other. If I study for my final, that's going to make me feel more prepared for the final. So studying does affect my feelings of preparation. When I roll an even number, that means I cannot roll an odd in that roll. If it's even, it can't be odd. So those two events as they are right now do affect each other, because if I roll an even, I can't get an odd on that same roll. So getting an even affects me not getting an odd. So then for the deck of cards example, if I draw an ace and I keep the card that I got on my first draw, now drawing a 2 has been affected because there's less cards in the deck. So a deck of card example could be independent or not. It would be independent if you replace the card. It's going to be not independent if you don't replace the card. Some other quick notes about independent events as it relates to being mutually exclusive. If two events are mutually exclusive, then they can't be independent, and vice versa. If two events are independent, then they can't be mutually exclusive. Students need to know how to do a question like this one, it's number 4 in the homework, in order to prove if things are independent or not. So as soon as they say independent, we know that we're going to be calculating the intersection of the probability of A times the probability of B. So let's go through the question and answer it together. Once you're done with this one, I would highly recommend that you attempt to do number 5, which relates to the same situation. Suppose you have a spinner with 5 congruent sectors numbered 1 through 5 and a 6-sided die that are both fair. Decide whether the given events are independent or not. Justify your answer using appropriate probabilities. So I'm going to start with event A. They have to tell you what your events are, otherwise you wouldn't be able to answer the question. Event A is a spinner shows the number 4. So I've got a picture here of a spinner for you with 5 sections, like they said, sections 1 through 5. If I land on 4, the probability of that is 1/5. 4 is one of the sections out of 5 total, so the probability of just getting the spinner of a 4 is 1/5. When we do event B now, we're going to use the spinner and the die and add them together, because that's the meaning of the word sum. So if the outcomes weren't listed here, that would be something that you'd want to do. I did the spinner first and the die second. Keep in mind that you should be able to predict in advance how many outcomes to expect. If the spinner has 5 sections and the die has 6, we should be expecting 30 total outcomes, which is what I wrote. So I have 30 outcomes of a spinner with 5 and a die with 6. Now let's find the sums that are over 6. So I'm going to find the 6's, looks like they are right here, and I'm going to find everything to the right of that because those will be bigger than 6. So I'm going to circle all of those. As soon as I get to a 6, I'm going to stop because I don't want those included. Oh, and I circled one that I shouldn't have. All right. So now when we count those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of them are in event B out of the 30 total. Now eventually I'll need to multiply those two together and get a decimal. But before I do that, I don't want to forget to find the intersection or the overlap. And so for that, I'm going to use my highlighter here. Remember that the intersection is where A and B occur together. B is the ones that I circled in blue. A would be me trying to find anything that I circled in blue that shows a spinner with a 4. So the spinner shows a 4 in this row, but the ones that are in that intersection are here, 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 and here. The spinner is the first number. Anytime it's a 4 is the one that I want to count. So I got 4 out of 30 for the intersection. That's where I'm showing A and B together. So now I'm going to use my calculator and I'm going to divide 4 divided by 30. And when I do that, I get 0.13 repeating. Then I'm going to take 1 divided by 5, which is 0.2. I'm going to take 15 divided by 30, which is 0.5, and I'm going to multiply those together, and that's going to be a 0.1. So what we've discovered here is that the probability of A times the probability of B is not equal to the intersection of the two elements. So that means these are not independent. If you wanted to say dependent here, that would also be correct. I'd highly recommend that students attempt to do question number 5 right now in the homework, because that matches real closely with what we just did.